Hello, and welcome to this episode of State Machine Corner. Episode 5, The State Machine Strikes Back. I'm Dr. Bruce Powell Douglas, Principal at A Priori Systems, and Senior Principal Agile System Engineer at the Martin Corporation. This episode will consider nested states, which are a powerful feature in UML and SysML state machines. A composite state is a state that has internal states. A nested state is a state that's nested within a composite state. Some people like to use the terms super for composite states and sub for nested states. I don't, because super and sub have distinct and different meanings in object-oriented technology. So I prefer the terms composite state for the enclosing state and nested state for the state inside a composite. Nesting allows you to consider subconditions or substates within a state. These are subconditions, nested conditions. So for example, I could be in North America or in Europe. These are or states. I'm either in North America or I'm in Europe. Can't be in neither. Must be in exactly one of them. Within North America, I might be in Canada or the United States. Those are the only two options in the model. Have to be in one of them. Those are or states within the context of North America state. Within the U.S., I can be either District of Columbia, Maryland, or Virginia. Those are or states in the context of U.S. Now notice that if I'm in Virginia, I am in the state of U.S. And if I'm in the U.S., I'm in the state of North America. That is simultaneously true. And in Virginia, I could be in Roanoke, Fairfax, or Arlington. So when a part, or an object, in SysML terms is called a part, is in a nested state, it's still considered to be in the composite owning state as well. Within a state context, such as US, those states, DC, Maryland, and Virginia, are considered to be OR states. It must be in exactly one of those states. You can consider nesting states to be different levels of abstraction on your state machine. Within the level of abstraction, you have a set of OR states, and the object must be in exactly one of those states, provided that it is in the composite state. At each level of abstraction, you must identify the default state, unless there's only one such state. If there's at least two, you must identify which of those is the default state. Now, UML and SysML state machines allow actions to be placed in various places. You can have exit actions, or executed when you leave a state, transition actions when you take a particular transition, or entry actions when you enter into a state. But what does this mean in terms of nested states? When you're going out through a level of nesting, you execute the exit actions from innermost to outermost. When you go in through a level of nesting, you execute the entry actions from outermost to innermost. Let's look at an example. So here we've got Cameo. In this video, I'm just doing the video in Cameo because it is essentially identical to how you do it in Rhapsody. There's a little bit of a difference we'll talk about toward the end of the video in one particular case, but it's not really relevant to the main thrust of today's symposium. So here we've got state, which contains state 10, which contains state 100. So we have three levels of nesting. And here we have state 2, which contains state 20, which contains state 200. These states 1, 10, and 100 have exit actions specified, and states 2, 20, and 200 have entry actions specified. So I expect, based on the rules we just talked about, if I execute this, I execute the exit action from state 100, then the exit action for state 10, then the exit action for state 1, then the transition actions, then the entry actions on the way in, state 2, state 20, and then state 200. Let's see what this actually does. So I will run the simulation. So we're currently in state 100 and in state 10 and state 1. Notice that we didn't specify the default state because there's only one option. If there were two states that were peers or states, we would need to specify which is the starting state. So let's now take our transition, EV1, and let's see what happened. We executed the innermost exit state here. Then we executed the middle exiting action. Then we exited the outermost state and did its exit action, outermost, followed by the transition action here, followed by the entry action from outermost to innermost. So outermost, middle, followed by innermost. So it behaved exactly how I expected. Let's consider an example. The example we'll consider is that of an automotive shifter, shown here. So here we've got park, we've got reverse, we've got neutral, we've got drive 1, drive 2. Drive 2 is L here. There are some basic rules in the state machine that we want to enforce. For example, when the car is off, we can switch it on. It goes into the parking gearing with the wheels locked, and you should be prevented from removing the key. When the car is on, the back light should be lit so that you can see what state you're in even in the dark. From park state, you can transition to neutral, forward, drive 1, or reverse. From drive 1, you can shift to drive 2 and back. From park, forward, or reverse, you can shift to neutral, which disengages the gearing. From neutral, forward, or reverse, you can shift to park as long as the car's speed is essentially 0. You wouldn't want to shift into park and lock the wheels if you're going 80 miles an hour. It would be bad. So essentially 0 doesn't mean it's exactly 0. It could be a tenth of a mile an hour, a half a mile an hour, whatever 0 seems like. But as long as it's close enough to 0, to be considered 0, we can then shift from any of those gears to park. When in park, wheels are locked. Otherwise, wheels are unlocked. When in neutral, gearing is disabled. If you're in one of the forward gears, drive 1, drive 2, gearing direction is positive. In reverse, gearing direction is negative. Drive 1, drive 2 use different gearing ratios. You can only turn the car off from park. When the transitions to off, then you can remove the key. So let's see what this looks like as a flat, normal state machine in Cameo. So here we see we're in the car off. We've got park, we've got forward drive 1, drive 2, neutral, and so on. When we enter, we have this. These are all opaque expressions, so they just do print statements for the purpose of this exercise. First thing we do is we unbacklight. When we transition to park with the car on event, we transition to on. We disallow removal of the key. We enable the backlight, and we lock the wheels. Once we're in park, then we can go either forward, where we unlock the wheels, and go to drive 1. We set the gearing direction to forward, and we set the gear ratio to drive 1 gearing. We can go to neutral, unlocking the wheels, or we can go to reverse and lock the wheels. From any of these states, I can go back to park from reverse, from forward drive 1, forward drive 2, or neutral. But I only want to go to park if the speed is essentially 0. So we've got a guard here. This is the guard is written in Groovy, the Groovy language, as the action language. So in the math library, you've got absolute value function, takes the local value property speed, takes the absolute value of that, and if it's less than some zero speed tolerance, it might be a mile per hour. We say it's close enough, we can go into park. So if we're in, for example, drive 2, and we get the to park event, only if this guard is true, only if we're essentially stopped, can you go to the park state. Otherwise, the event should be thrown away. We can also go to neutral from any of these states, reverse, park, drive 1, drive 2, with the go to neutral. And what this does is it disables the gearing. Now to go back from, say, drive 2 to drive 1, from neutral, we want to make sure the speed is greater than or equal to 0. What we want to avoid is we're in reverse gear, going minus 10 miles an hour. We go to neutral, and then we immediately shift to forward gearing. Now remember, at this point, we're going minus 10 miles an hour. That would be bad for the transmission. So we can't do that if speed is greater than 0. Unless speed is greater than 0. So if we're going minus 10 miles an hour, go to neutral, we can go back to reverse. Speed is less than or equal to 0. That's okay. But we can't go to forward gearing until we've dropped speed. Once we're going 0 miles an hour or positive miles an hour, we can go back to drive 1. So this represents that behavior. Let's run this and watch it work. So we'll simulate with context because we've got a couple of value properties, speed and 0 speed. Here we see speed is currently 0. 0 speed we set to 1 mile an hour, so that's close enough to stop that we'll consider that stopped. We can run this and we'll start in car off. We see the shifter backlight is off. We can then go to car on. And we go to the park state where we've disabled removal of the key, we turn the backlight on, and we've disabled the gearing, and we've have locked the wheels. From here, we can go into drive 1 with the forward event signal. We go there, and we see that we've unlocked the wheels. We've set the gearing to the forward direction, and we've set the gear ratio to drive 1. From here, we can go to drive 2, to event. From here, let's say we're going 10 miles an hour. Now, I would expect that I could go back to park, except that I'm going 10 miles an hour. So let's make sure that that functions properly. Let's try taking that event. Transition. So we'll go to park, and what I expect is nothing to happen, and in fact, that's what happens. That event is discarded because the guard fails. If I go to a small speed, less than my 0 tolerance, 0.2 miles per hour, now I expect that to work. And in fact, we see that's what happens. I go into park, we've locked the wheels, and we're in park. Life is good. From here, I can go into neutral, let's say. I can go to, let's go to reverse. In this case, let's go to reverse. We can set our speed to say, minus 0.1 miles an hour, inching backwards. From here, we can go to neutral. And we disable the gearing. We can go back to reverse. That's fine. And from here, we can go to park because, again, speed is less than that band. And finally, we can turn the car off by going to the off state. And we can now remove the keys. Key may now be removed, backlight is off. So this works as we expect. Now, what would happen if we model this using nested states? Well, let's do that. Let's go ahead and stop our execution, and let's look at what it looks like as a nested state machine. Now previously, we had 8 states and 19 transitions, including the default transition here. If we add nested states, we've got also 8 states, including the composite states, and we've got 13 transitions. So we've reduced from 19 to 13 transitions for exactly the same behavior. Notice, for example, that this toPark transition is only one of these, and it goes from the composite state. So as long as the car is on, if the toPark signal is received, the part will transition to the park state. And here's our guard. So before we had several of these. In our flat state machine, we had toPark here, 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 and here. And in our nested state machine, we only needed this once. So our state machine is more parsimonious. Similarly for neutral, there were several ways we could get to neutral in our flat state machine, to neutral, to neutral, to neutral, and to neutral. In our nested state machine, we only need that transition once. So we only need to represent the transition a single time because we're going from the composite state. And it applies to every nested state, whether it's park, it's reverse, it's drive 1, it's drive 2. These are all nested within car on. As long as the car is on, if we get the to neutral transition, we will transition to the neutral state. And the other events are much as they were before, other than forward has 2 nested states, drive 1, drive 2. Notice that at both levels of abstraction, we've got the nested state machine for car on. We identify the default as park. But then forward, we identify the default as drive 1. Does this execute the same? Well, let's see. So we'll run our simulation, run with context. And we start off in the off state. And we see the backlight is set to off, just as before. We can now go to car on. And we execute our actions along the way in. So we do our transition actions, can't remove your key, followed by the entry action, backlight is on, followed by lock wheels, which includes disabling the gearing and locking the wheels. So exactly the same behavior. Now let's go forward, and we enter into the drive 1 state, and so we unlock the wheels, we set our gearing to forward direction, and we set a gear ratio for drive 1. We can go to drive 2 by doing a D2, and now our gear ratio is set for drive 2. So now let's try taking this transition with the speed set to 10 miles an hour. Previously, it properly discarded that event and didn't do any behaviors because we weren't going essentially 0 miles an hour. We expect the same thing to happen here. Let's see what happens. So we'll now enter the event toPark, and we see nothing happens. So that's exactly right. If we set our speed down to some small value, 0.2, let's say, and repeat that, we should now be able to take that transition. And we see that the gearing disabled, wheels are locked, we're now in the park state. Good. So now we can transition to reverse as we did before. We'll set our speed to minus 0.1 miles an hour, or inching backwards. We can go to neutral. Take this transition here to go to neutral. In fact, we see they take that transition, and we've disabled the gearing. Now we can go back to park, because we're, again, still going essentially 0 miles an hour. We can go to park and take this upper transition. And finally, we can turn the car off. And now we can remove a key. So the behavior is identical with a smaller number of transitions. Let's consider a case where we want to add a feature to the system. We want to add the feature that allows us to have an emergency occur, which puts on the emergency brake. And if the emergency brake is on and the speed is zero, essentially zero, then we can also block the wheels and go to this emergency lock state. Otherwise, as we apply the emergency brake, we will transition to emergency stop only when speed is back down to essentially zero. What would that look like in our flat state machine? It looks like this. So let me zoom in a little bit. You see that a little better. So from reverse, neutral, park, drive 1, drive 2. If we get the EV emergency event, we go to emergency state and we have a behavior to set the emergency brake. Now there are two cases to get to emergency stop. Either when we enter, the speed is already essentially zero, in which case we transition immediately to emergency stop. Here's this transition. It's null triggered. There's no triggering event here. But there is a guard. So this guard evaluates to true is because we're going essentially 0 miles an hour. And you can immediately transition to emergency stop. However, if we're moving forward, it might take time for the emergency brake to slow the car down. In that case, we want to transition as soon as we're essentially going 0 miles an hour. And for that, we're going to use a change event, indicated by when. So Cameo indicates a change event. Rhapsody does it in a slightly different way. In a subsequent video, I will talk about change events in more detail. So this transition will fire when this becomes true, once we're in the emergency state. So let's see if this works. So let me zoom out a little bit, and let's run this. All right, we're now running our simulation. Let's go on, turn the car on, and the behavior we expect to see is on. We're now in the park state. Let's go to, say, forward. Now we're in the drive 1 state. Let's set our speed to 20 miles an hour. And now let's have our emergency. So I have our emergency. We transition into the emergency state. We see it's highlighted a little hard to tell with all the red. It's highlighted here. Emergency state. But we have not transitioned to emergency stop because the value of speed is 20. What if I set the value of speed now to, say, 0.1? 0.1. Now we take the transition to emergency stop. Gear is disabled, wheels are locked, and emergency brake is set. To do this, we added 2 states and 7 transitions altogether to make that happen. What if we did this with a nested state machine? This is the nested version of that same state machine. Notice that we added our 2 states. Well, we only needed to add the EV emergency transition a single time. So previously we had 10 states and a total of 26 transitions. And now we have 10 states and a total of 16 transitions. We only had 3 transitions to do exactly the same behavior. But let's make sure that it behaves the same. So let's go ahead and run this. And we'll do the same case that we had before. We'll turn the system on, turn the car on. We'll then go forward. We'll set our speed to 20 miles an hour. And now we'll have our emergency. So I'll insert the emergency event, EV emergency. And we transition here, and we see that the set emergency brake is on, gearing is disabled. That's good. Now we can set this back to, I think, 0.2 that we had before, and we take the transition finally off to the emergency stop state. So it behaves exactly the same way, with fewer transitions, and I think less overall complexity. So now we've seen nested states and how they can simplify your state machine. I believe that there are essentially two different kinds of complexity. There's what I call essential complexity. That's due to just how hard the problem is to solve. And then there's inessential complexity, also known as incidental complexity, which is due to how you've chosen to solve the problem. Good designs take inessential complexity as close to zero as possible. Essential complexity is what it is. We reduce the overall complexity to as little as possible. The use of nested states can do that, not in all cases. So whether it applies to be a good best practice in your particular state machine depends on whether or not it simplifies the state machine. But this is a powerful tool for rendering complex behaviors in a very simple, straightforward way. If you like this video, please click the like button. If you want to subscribe to be notified when additional episodes of this channel come out, click the subscribe button. I hope this was interesting. If you want to know more, I've written extensively on this and related topics. You can also visit my website for presentations and models and papers, and there's a forum. It's all free. Feel free to come on down. With that, I hope you have a very nice day.